I would like to welcome George Waldbusser, who is going to talk a little bit more about the substrate inhibitor ratio and some of the complexities that result from there.
Okay. Thank you, and I want to thank the organizers. This is really a fun topic to talk about, and I will try to get through all these slides that I have. Talk about calcification and mostly bivalves, but thinking a little bit more broadly. So just some key background. We know that thermodynamics and kinetics drive abiotic calcification. We know it's a surface controlled process, and so you saw that a little bit with previous talk, that there's a surface that that minerals precipitate onto. And we also know that carbonate ion is not the only substrate that's used, right? So even in a saturation state perspective, we know that that's not the only thing that they need as a building block. And as Andrea pointed out, calcification produces protons as a function of how much carbonate ion that they're using. And we also know that organisms are sensitive to multiple stressors, right? So anything that affects the organismal physiology could potentially affect calcification. So that's a perspective to keep in mind, is that there are many things that can affect the overall health or fitness of the organism. And what we're trying to do is understand and separate some of these impacts. And I'll also say that saturation state and SIR don't have to be mutually exclusive. We've sort of argued this from the start, but I think it's almost a false debate in some way to think about it as it's either got to be one of the others. Okay, and I like this quote from F. Scott Fitzgerald, that true intelligence is the ability to hold two opposing thoughts in your mind. I think we would do good sort of keeping that in that perspective. So just quickly, Andre did a great job presenting this, saturation state and SIR. And then keep in mind that the proton concentration, or pH, is largely a function of the sort of acid part of the carbonate system and the base part. And this is the reason that this controls pH in the ocean is because this is the largest by concentration acid-base pair in the ocean. So that's what fundamentally controls pH in the ocean. So one way to organize our thoughts about this is to think about these different systems, and people have sort of put these different types of calcification, extracellular, intracellular, intercellular, as ways to kind of organize the way we think about this. And we know that some of these organisms switch and can do these different types of calcification. So just to highlight in general, some people sort of put this as an intercellular for corals. Bivalves are often, or mollusks are thought as extracellular, where the difference is the tissue is inside the body and the shell is on the outside, but there's still these calcifying spaces that have different levels of connection to the outside environment. And then this is a picture of foram. And so would we expect one simple answer? Because we have all these different ways that organisms make shells. It's going to be a very unsatisfying talk if you expect me to say it's only this or that. Okay, so here's one. This is Hans Portner's sort of perspective on the biology around calcification. And you'll notice there's lots of protons and transport processes. And so this sort of model, calcification surfaces are extracellular. Everything's linked through metabolism, and internal acid-base chemistry is the key. We know that within cells, nearly every animal regulates the pH very closely, and the blood, or the stuff that circulates around the outside of the tissue or within the tissue, has different levels of regulation. So what happens inside? We saw one picture of this very nice paper by Wei-Jung Kai. And so I just want to show you another sort of diagram from here. If you look at, this is the DIC, the seawater, outside and inside relative ratios. And so right across this interface into the calcifying fluid, you'll see the DIC drops, the alkalinity goes up, and the CO2 goes way down. So what they sort of argue in the paper is that passive CO2 diffusion helps supply the carbonate that's ultimately used. And actually maintaining a lower DIC concentration in the calcifying fluid makes it easier to maintain a higher pH because there's less protons to buffer. This was a really nice paper on mussel larvae, and they found that the larvae do regulate or elevate the pH and saturation state at the site of calcification within these larvae. But as acidification worsens, that sort of goes away very quickly. And this is just from that paper. This is showing the amount of calcium in the shell over time. And you'll see, and I'll talk more about this rapid calcification that occurs during early development. And then finally, there's a paper that people sort of often forget about. There's a nice paper. It was actually, I think, right over here at MBL that was done. They measured pH and the DIC in adult bivalves and found that despite the pH being what we would consider low for the ocean in the calcifying fluid, those DIC concentrations within those calcifying fluids was nearly twice seawater. So if you calculated the saturation state, it was actually fairly well saturated. Okay, so I'm going to make a case for kinetics. We think about thermodynamics a lot. We talk about saturation state. So some of you who think about kinetics and thermodynamics might know this analogy, but the idea is that there's the same amount of energy included in a hand grenade and a donut. That's a thermodynamic perspective. The kinetic perspective is one blows you up more quickly, right? Okay. All right. So I'm gonna sort of try to frame this in fast and slow growers and get to this idea of why some things might have a saturation state sensitivity. This was a paper, Steve Gameau and others, and what they found in their paper tried to look at what actually regulated the responses to acidification, and what they generally found was that slower growers are more resistant, or slower calcifiers are more resistant to ocean acidification. This is actually a really nice paper on polychaetes. And what they found was that brooding polychaetes were found to be more resistant to ocean acidification. Now, one of the interesting aspects about brooding versus broadcast spawning invertebrates is that brooders tend to create fewer gametes or offspring. And so from an evolutionary perspective, the way we often think about it, you might think that since there's fewer offspring, less adaptation potential there. And what they found was quite the opposite, so that the brooding organisms actually, even though hold lower genetic variability, they were more resistant to ocean acidification. So what it comes down to is that with the greater genetic variability from a broadcast spawner might allow potential for adaptation if the life history traits that provide for that broadcast spawning compromise fitness to a specific stressor, then you may be SOL, so to speak. Okay, so the saturation state sensitivity that we've talked about, it's all framed in the sense of kinetics. It's not thermodynamically driven. It's not a lack of carbonate ion availability. I'm going to show you some more data later in the talk. But this is basically trying to look at calcification rate. This was sort of earlier work we did in one of the oyster hatcheries. And so what this demonstrates is a really high rate of calcification since in that early period when they first build their shell, and then that calcification rate drops. These are 3 different cohorts of Pacific oyster larvae. What we can do is take that rate equation for calcification and rearrange it and say, what if we take kind of the average condition for later larvae and the average condition in the early larvae, and then solve for the K. So this is the rate, saturation state. We're going to set the rate order to 1 to make the math easy. And then say, what sort of constant do we need to support that calcification rate as saturation state varies? And what you'll notice is that at the higher calcification rates, this line, or this K value, has to increase exponentially to support that, right? It's just simple math. There's nothing magical about it. And what people get wound up about is that this clearly isn't the equation that's defining the rate of calcification, but it's the constraint on the system, right? We know that there's a physical chemical constraint that has to rely back to this equation in some way or another. So I always use this analogy. We know gravity exists, but birds fly, right? It's a constraint. They figure out how to do it. They figure out, and that's what biology does, is overcome these constraints that are out there in the physical chemical world. Okay, so here is Pacific oyster larvae, 10 hours post-fertilization, 16 hours post-fertilization. And the take home here is that in this 6-hour window, they build their entire first shell. That represents about an 80 to 90% increase in calcium carbonate per body mass. So it's incredibly rapid calcification, and then we actually looked at using some stable isotopes to understand some of the dynamics of the calcification. So this is del 13. What you're looking at here is the shell signal. This is the seawater signal, and then this is basically a mixing model we use to look at how much metabolic carbon goes into the shell during these stages. And so what you'll notice is days since fertilization is about, very early on, about 6% of the shell is actually made from metabolic CO2. And as they progress out later, a much higher proportion of that is metabolic CO2, despite the fact that during this early development, we know they have exorbitantly high respiration rates to support all this development. You can look at this in the tissue as well, just to get some idea of the energetics. So We know they carry over the metabolic carbon from the eggs, right? And so here's the tissue value, here's the algae. It's sort of interesting working hatcheries where they're using industrial CO2 to grow cultures. That's why you have such a negative number here. That's not natural sort of environmental algae signal. And so what you'll notice is that the metabolic carbon in the tissue from the mother sort of drops off really quickly. We have nitrogen isotopes that show this varies as well. So we know that they're carrying this energy from the parents. They have a limited time and a limited amount of energy they start with. And we know that this calcification is very rapid. And what we infer from, I knew I was going to do that. We infer from this graph is that the amount of metabolic carbon increases over time, which suggests that they're able to better isolate the calcifying fluid later. Because the respire carbon is going across those tissues into that calcifying surface. Okay, so there's been other experiments to understand this, sort of what's actually controlling calcification. As we were setting up and running our experiments, Gazot published this paper. They argued the carbonate ion concentration was key variable, not saturation state, because they doubled the amount of calcium in the water at low saturation states and found didn't help them. Soon after we published our paper, this paper came out by Thompson, and they argued SIR was the key variable, not saturation state. We know, however, it's all correlated to saturation state, so that's sort of the problem. So I'm going to walk you through some of these, the experiments quickly, and then get to a way that we can actually disentangle the SIR and saturation state. Okay, so here's what we did with these experiments. Effectively, you can decouple the carbonate ion from these other parameters more or less by playing around with the DIC concentrations and the relative amounts of alkalinity, so the ratio of DIC alkalinity. Well, you'll notice this is from one of several experiments we did. These are different treatment conditions we generated, 2 different experiments, so we can create a PCO2 that's fairly constant over a wide range of aragonite saturation, and vice versa, and these lines are lines of equal pH. And so what we did then with the bivalve larvae is measured several things. I'm going to show you primarily the shell development and shell length of the normal larvae in these experiments. So here's what the data looks like. Just to remind you again, so this is during this rapid period of development, so it's the first 48 hours. And what you'll see is that the darker values are lower saturation states. And so I plotted it versus PCO2, pH, and saturation state. And you'll see that we get good development, so the proportion normal down to very low pHs as long as the saturation state is high. And this is the shell length of the normal, and basically no pattern there. And interestingly, you see almost a negative effect of the pH. And actually what this comes back to is that to create these conditions, we have to lower the DIC content. So here's actually an indication that the DIC might be important for some of the shell length, but not development. Oh, and then finally, we wanted to check on this calcium addition. So we actually added calcium at supersaturation. And this is what you get if you add too much calcium to the water. So the inference that adding the calcium didn't make saturation state important was problematic because they never did a control at a high saturation state. So it turns out that too much calcium is bad for organisms, which isn't surprising, the role it plays in physiology and so on. Okay, so we've done this on a number of species, 2 different species of mussels as well, found basically the same pattern. We found that if you look at respiration rates respond to pH. And we have some evidence that the initiation of feeding when larvae develop actually is correlated to PCO2. So now all these different variables are actually having their OA is a multi-stressor in itself, right? So trying to understand how this all propagates to the physiology gets a bit more complicated. So now I'm going to show you some data from Olympia oyster larvae. So these are native to the west coast of the US. They're brooded species, so that's your first foreshadowing hint. And what we find is that despite a wide range of conditions, really no response of these larvae to saturation state. And one of the challenges was we had to actually grow these organisms in these early developmental stages outside the brood chamber. So part of the challenge was getting females with fertilized eggs before they started to calcify, removing them, then putting them into the experimental conditions. And then we also ran controls for the brooded, and we found more or less similar conditions. So despite being vastly undersaturated, they developed fine, and almost looks like it was bad to have too much or too high a saturation state, and really no effect on size as well. And again, 2 different experiments here we ran. And so one of the things that was notable is if you look at those developmental stages, it takes about 24 hours to go through that initial calcification, so about 4 times longer to go through that step relative to the Pacific oyster larvae. So we did was try to measure actual calcification rates. And so you'll notice these are nanomoles of calcium per millimeter square of shell. And again, we did this because the larvae are different sizes. And so in order to actually try to standardize across, because the Olympia oysters actually have a higher total amount of calcium they're incorporating, a larger shell. And what we see is about an 8-fold difference in the calcification rate during the initial calcification in the Pacific oysters and in the Olympia oysters, and this is something we can talk more about later. I still haven't quite figured out what happened here, whether that was a real analytical outlier or if there's actually some process where they're kind of gathering stuff and then putting it all into the shell. What we wanted to do is try to look at what kind of effect or what's their energetic budget that's occurring during this time. So we measured lipids in these organisms. So this is basically energy lipids versus structural lipids. So this is the phospholipid bilayer. This is all the energy that they have available. And in the Pacific oysters, what you see is a nearly 40% decrease per hour in that energy lipid relative to the structural lipids, and really no change in the Olympia oyster in their energetic content. So I've sort of phrased this as a slow shell movement, right? So slow shells might make them more resilient. And what's really interesting is we've had sort of a discussion and people going, well, they grew up, they're sort of evolved to live in this upwelling zone, naturally elevated CO2, or because they're brooded in a chamber, so there's respiratory CO2. I think that there's probably another reason the brooding evolves, ecologically speaking. And so it turns out that maybe this brooding evolved for another reason, and that's actually what's conferring them some fitness or resilience to acidification. And that's something that Stephen Jay Gould sort of called an exaptation. So this is kind of the overhead or the messiness in biology. So there's things there that might provide resiliency without having to have direct adaptation and selection. Okay, so I got 3 minutes left to cover the rest of this. So then we still haven't disentangled SIR and omega, right? So here's one way to do that. If we took a certain seawater property, or certain seawater, and we just change the temperature at 400 microatmospheres, we see that the SIR is temperature insensitive, but saturation state is not. We can add CO2, so then we can create a couple conditions where we have constant SIR and varying omega, but we see it's hard to get these things to line up. So what if we change the DIC, and sort of Andrea alluded to this earlier, we can create all these different conditions and ultimately get a matrix where we have constant saturation state, varying SIR, and vice versa. So that's one way to do this. Unfortunately, we haven't gotten funding to do this yet, and I won't say anything else about that proposal. So then, since we know there's this temperature sensitivity, we can use a Q10 to back out, because if we're changing the temperature, we expect vital rates to change. So we back out the vital rate temperature effect and then look at how things respond to these two different parameters. So I'm going to jump through this, and just to get you to the punchline here. And we had to go through and look at a bunch of studies that were already published, and we had to find temperature and CO2 treatments that had some covariance in them. We had to fully constrain the carbonate chemistry. We needed non-harmful temperature treatments, more than one, right? Which is not something people frequently do in these sorts of things. Everybody wants to hit things with a hammer to show an effect. So you don't see a lot of studies where people try to look at these intermediate values. And we have to have some rate measurement to correct the temperature effect. So going through Christy Croker's database has been involved with this. And then a literature search after that, is when we did this about 2016, we found 7 whole studies out of all the OA literature. And I apologize if we missed one of yours, but it's quite shocking when you realize how few studies actually hit these criteria. These are those studies, and so you see it covers a range of taxa. And so let me show you some of what the data looks like. So if we plot the SIR and saturation state, you'll see that they're generally correlated, but there is some variance because temperature differences and so on in these experiments. If we look at decompose the SIR into its components of proton concentration and bicarbonate, you'll see that largely the variance comes from proton concentration. So then is it really a question of pH we're looking at versus SIR? That's something we're still sort of talking about. So I'm going to show you 2 examples, one from coral reefs. There are 2 different studies here. Silverman et al. Paper in 2007. And so I'm showing you two sets of data here. The black dots are the actual measurements, and then using a Q10 for the coral, we sort of correct the rates, and there's the SIR response and the aragonite response. So it's difficult to fully disentangle these, but what you'll notice is that the fit is better with the saturation state versus the SIR. The Langdon 2007 biosphere experiments, we use those as well, which are interesting because they actually use bicarbonate addition to alter the chemistry, and we see a slightly better improvement in saturation state. I'll show you with work that I led years ago, fitting a nonlinear curve. I know they look similar, but the fit is far better with the saturation state. And if we go through all the studies, we generally see that saturation state ends up resulting in a better fit of the carbonate chemistry than the SIR. And Andrea pointed this out, but we know dissolution is driven by saturation state. So, okay, so the answer to any of this or that question? Yes. Right? We know that. So, let's move forward from the debate about it can't be this or one thing's a myth or not, and understand how these different things interact on the physiology and biology. And then just a few things to do. I've realized nobody really likes a centrist. And I don't think we really want to rely on existing studies and reanalysis to make this argument. We need specific studies designed to do this. And from a global carbon perspective, maybe it won't matter a whole lot, but locally it's going to be really important for corals and bivalves especially. Most of the variance in SIR is from proton concentration from what I've seen. So is it just pH? Can we sort of move forward from that? And we know that OA has multiple modes of action, and there's always something else, right? So temperature, pick your pollutant, you can find a way that's going to affect the physiology and have some effect on calcification. So I'm going to end there, and we have a couple minutes for questions.
Questions? One or two? Oh.
This is Andrea Fossbender. That was great. It was really interesting. I also liked your quote about OA as a multi-stressor in itself. My question, because you did this literature search, I know you're advocating for redoing studies, not relying on the literature, but you did have quite a few different organisms, like taxa,
Yep.
and I thought that was quite interesting. And so it would be interesting to know if you saw differences in those relationships, because as you mentioned, different organisms are very different in their calcification
Yep.
approaches.
Yep.
So I was just curious if you could speak to that.
Yeah, and so I think it's a great point. And so, yeah, we could look at that, but, in many cases with one study for one organism, and often the treatment levels are set differently, temperature ranges are different, and what we have to hope for is that in those studies that there's sort of non-lethal or non-negative effects of those things. So I don't think at this point we can easily say that, in one case or the other, but I'd expect even across life history. So the saturation state sensitivity that we see in the larvae, in bivalve larvae, that may not hold up as much in adult larvae or adult oysters or shellfish because they don't have to grow as quickly. In larvae, they have developmental timelines they have to hit, otherwise it's sort of they're done. So.
Will Barrelson, USC. USC is the key. Donald Manahan at USC and his postdoc students done this very interesting work, I think, on the energetics of calcification.
Yeah.
I wonder if you can comment on their findings that there's no additional cost to calcify this initial shell, whether you're at omega-3 or at omega less than 1. That's really fascinating, I think.
Thank you for bringing that up. So the finding basically is that, all these impacts that we see on these larvae, that there's no energetic cost, right? If you look at their data in the larvae they used, the sizes of those larvae were 50 to 75% smaller than what's in the literature, and the lipid values in those larvae, for everything else that's been published, was sort of astronomically small. So I think, unfortunately, it was what they're arguing. And I've seen this in a number of papers where we don't think very carefully about the condition of the critters when we put them in experiments. But the condition of those larvae look to be so compromised that there's no scope to see a response to ocean acidification or even an energetic change because there's no energy there to start with. So, I've talked with Donald about this before, and they've sort of said, it's tough, and it's tough because you put time into these experiments, and then you see these things after. But it's a bad indication that their controls were 50% to 3/4 smaller than everything else out in the literature. So that's where. And I don't understand from any scope for growth perspective how a stressor that we understand can actually not have any energetic effect. It goes against everything we understand about larval.
I think their argument is that they have a store of energy that's calcified.
They do.
But then they don't have energy to maintain other life functions quite as well.
Well, the energy, right, what we understand with bioenergetics is that they have an energy pool that controls everything, right? And so it can go to tissue growth, it can go to calcification. In adults, it can go to reproduction. And so if one of those things is pulling more energy from the pool, then there's less for something else. And every other study we've seen shows effects of size or development on larvae. And so, again, if you don't have very much energy to start with, you can't find an effect on the energy stores by putting a stressor on there because they're already stressed.